Welcome to my classes on fundamentals of electrical circuits. And fundamental to almost all electrical engineering happens to be transients. So I am discussing some aspects of transients first here, most of the basic aspects. Transients happen to be at the nerve center of every happening in electrical engineering. And they are the outcome of two elements. One is the capacitor and the other is the inductor. Sometimes they work together, in which case whereas the inductor is offering the energy or releasing the energy, it's the capacitor which takes it on. Similarly, when the capacitor releases the energy, it's absorbed by the inductor. On the other hand, if they work separately, then it's a different picture altogether. We have the resistors expending the energy that is being released by the inductor and capacitor. So they offer several interesting questions, and this is what we are going to see in the coming questions and transients. First, we deal with the basics, wherein we try to think in terms of how the elements respond to DC first, okay, and then when a DC is applied, as also when DC is removed. So let's look at problem number 1, which shows a large number of elements, but it's a very simple problem because very simple concepts are involved. In this problem, we see that there are two sources, both of them being independent sources. One is a current source, the other is a voltage source. There are several inductors, L1, L2, L3. There are similarly two capacitors, C1 and C2, and there are three resistors, R1, R2, R3. And some of the answers are given which don't reveal themselves, which don't reveal any insights. So let's move on to reading the question. The circuit shown in the figure, the current source I is equal to 1 ampere, okay, and voltage source V is equal to 5 volts. So that's solved. R1, R2, R3 is equal to 1 ohms, okay, it's written as 1 watt, okay, let's call it as 1 ohm. L1 equal to L2 equal to L3, again 1 Henry, and C1 and C2 equal to 1 farad. The current in amperes through R3 is asked. R3 is in series with L3. And the voltage source V respectively will be. Okay, so voltage V is given as, and through the voltage source. Okay, so V is given as 5 volts. So what's the current through it? Okay, so this is what we are supposed to find out. Okay, when DC is applied, the overbearing rule happens to be that at steady state, all the inductors short out, especially because they obey the conservation law. So they cannot have a buildup of energy. So finally they absorb energy and then they switch off. So that's point number 1. Then they act as short circuit. Okay. Finally, the capacitors also collect all the charges that is possible, and thereafter they open out or they become open circuit. So in other words, we can say that at the beginning capacitor is a short circuit, and thereafter in steady state it becomes an open circuit. Similarly, an inductor in the transient zone, it starts off as an open circuit and then it becomes a short circuit. There are several other aspects with respect to inductor and capacitor which were discussed earlier, which will also come consequently. So here we have a steady state situation wherein the DC sources have resulted in opening the capacitors and short circuiting the inductors. So if we follow the path from I, we see that there is a short circuit, and then there is the irrelevant resistor R1, and then we have it. When you look at the path through capacitor C1, that's open, so the current cannot progress there. It goes on to R2, so it flows through the shorted L1, flows through R1 and then R2, and then it flows through R3 because L3 is a short. So this is the situation. Okay, so we see that there is a current flow path in only via R1, R2 and R3. The capacitor again has opened out, and so we also have the battery source V open to becoming charged via the current I. Okay, and so if you look at, okay, so that's regarding the status of all the elements. So what is the current through L3? Okay, so now since the L3 is shorted and R3 current is asked, we also realize that this R3 has a voltage 5 volt across it because the 5 volt source now becomes completely across it. So 5 by R3, which is equal to 1 ohm, that will give you the current through R3, which is equal to 5 ampere. Okay, so and B, C and D offer 5 as the correct value. Okay, so that's okay. Now we move on to what's the current through the 5 volt source. So now since 1 ampere has come in from the source, and it has flown to R through R1 and R2, and then proceeded to R3 as 5 ampere, because it is V by 1 is equal to 5 ampere. So 4 amps has now got to come from the 5 volt source. Okay, so it's not charging, it is also discharging. So both the resistor, both the current source I as also the voltage source are now feeding R3, because that's the only line of flow of current. So it means that the current current flowing from the voltage source is going to be 4 amps. Okay, so answer D is correct, because 5 amps now is flowing through R3, and it has 1 ampere contribution from the current source and 4 ampere contribution from the voltage source. Okay. So now we move on to second problem, wherein the time constant is asked. Okay, so before we look at the series, the theory behind it, let's have a look at the diagram of the circuit. Okay, so we have a 3 ampere source, and we have a network of capacitors on the other hand, as also 2 resistors, 3 ohms each. Okay, and then the capacitors, as they are put, you can assemble them all together into C effective. What is C effective? Where 1 farad and 1 farad are in parallel, which is equal to 2 farad, and 2 farad is in series with 1 farad, which is 2 into 1 by 2, 2 into 1 by 3, or it is 2 by 3 farad. So now this is the situation. Okay, now let's read the problem. The time constant for the given circuit is. So let's start from how we assess time constant. Time constant is the time wherein the inductor or the capacitor is so active that it discharges its energy. Okay, almost all of its energy within that particular time frame. Okay, that's what is time constant in the practical understanding of it. Okay, so how do you assess time constant? You have to kill the sources. So there's only one source here, and if you put the current source as equal to 0, it means that's an open circuit. Okay, then you look into the circuit from the inductors or capacitors perspective. So here we are having a C effective as given by 2/3 farad. Okay, so from its perspective, you look into the circuit. So what do you see? You see that since the source is open circuited, you see that in series we are having 3 and 3 6 ohms. Otherwise, it would have been in parallel, or it would have been short term. So 3 and 3 6 happen to be in series with respect to the capacitor, effective capacitance of 2 by 3. Okay, so now what is time constant? There are 2 ways for assessing it. If it is an inductor, if the effective inductor is looking back into the circuit, then we have L by R. Or if it's the effective capacitance which is looking into the circuit, then it's going to be RC. Okay, so C is 2 by 3, and R, as we saw, is 3 plus 3 6. So the answer is the time constant is 2 by 3 into 6, or it's equal to 4 seconds. Okay, you get them in seconds because it's time constant. Okay, so moving on to a series RL circuit, as is shown in the figure, we have the DC voltage V feeding RL there. Okay, and we have several answers given there. Okay, so V by L minus V by R equal to 0, and minus R V by L square. Okay, and what is asked is a series RL circuit is excited at t equal to 0 by closing a switch as shown in the figure. Assuming no initial conditions, the value of d square I by dt square at t equal to 0. Okay, here let us remember that. Okay, so earlier we talked about the time constant. Right now let's talk about how the inductor or the capacitor gets charged. Okay, if it is charging, it's always following the relationship of a current multiplied. For the inductor, it is a current multiplied by 1 minus e raised to minus t by tau, where tau is the associated time constant. And what is the current? Current is the final current that is going to flow through the inductor. In this case, it's given by V by R, because the inductor is going to be a short. Okay, once the voltage is applied, the resistor alone remains once steady state has arrived. Okay, hence now we realize that there is a steady state current flowing through the inductor, which is given by V by R, because the inductor is the short at steady state, and this indicates what is called as IL infinity, as is shown in the small box out there. That is, okay, and then this is further multiplied by 1 minus e raised to minus t by tau, where tau is equal to L by R. Okay, so this shows the exponential way in which the inductor becomes charged with the current. Okay, and finally becomes a short circuit. Okay, so this is the progress of the transient. Okay, And now what is asked is the second differential. So the first differential tells us that V by R, because IL infinity is V by R, is going to be multiplied by minus of minus R by L, because T has a coefficient of minus R by L, into again e raised to minus R by LT. Okay. The next derivative gives us, so of course R gets cancelled on the denominator, so it becomes minus V by, it becomes plus V by L. Okay. One more differential will give you us again another minus R by L, and of course at t equal to 0 it becomes e raised to minus R by L t becomes 1. Okay, so the final result is going to be minus R by L, V by L square, and so D happens to be the answer. Okay, so moving on to problem 4. Okay, so here again only two basics have been so far discussed. One is the time constant, which was applied in this problem, where we saw the charging of an inductor. A capacitor also charges similarly, but then it utilizes, it is the voltage to which a capacitor is charged, as is obvious because it is ultimately collecting the charges. Moving on to problem 4, here we see that we are having a 10 volt source. There's a switch. A switch always indicates that a transient is what is being assessed or computed. Okay. And then immediately it has a 3 ohm resistor, and then it has a capacitor 4 farad in series with a 4 ohm resistor. Parallel to it we have another 4 ohms and a 4 Henry inductor. So there are 3 parallel branches, and when the switch is on at steady state, it's clear that the capacitor is going to open out and the inductor is going to short out the whole thing. Okay. And let's see what is asked. Of course, from the different answers, the voltage is being asked is clear. So which voltage? Let's see. The circuit shown in figure, the switch S is closed at time t equal to 0. The voltage across the inductance at t equal to 0. As was mentioned earlier, the progression of the transient in an inductor is such that it starts off as an open circuit and becomes a short circuit. Unlike a capacitor, which starts off as a short circuit, why? Because it is getting charged, okay, and then it opens off. Once the charges once it becomes full of charges, it opens off. Okay, so this is what is happening physically. Okay, and so it's easy to understand. And so now we have the inductor which is at t equal to 0 plus, that is immediately after the switch is on, it is an open circuit. So it is trying to collect the voltage across it. So what's the voltage across it? The capacitor, as against the inductor, is a short at the beginning because it is charging. Okay. So now we are having 2 4 ohms in parallel by virtue of the capacitor being a short. Okay. At the very beginning, that is a t equal to 0 plus. So 4 and 4 in parallel gives us 2 ohms. And this 2 ohms along with the 3 ohms share 10 volt. So it's obviously 4 volt, which is going to be across the inductor, which is at this point of time an open circuit. I hope this is clear. So these are some of the things that will be juxtaposing often. That is, what is the status of the inductor at the beginning, at the end, the capacitor at the beginning, at the end, what's the time constant, okay, and how does it charge. Okay, so we talked about charging. Now regarding discharging, again it happens exponentially, but it becomes what is about what has to be discharged, that is, let's say V0 or maybe I0 into e raised to minus t by tau. The same tau, that is the same whatever is the circuit offers as the time constant is going to be tau again. So moving on to this problem number 5, a unit step voltage is applied at t equal to 0 to a series RL circuit with 0 initial conditions. So it's an RL circuit to which this circuit is applied. It is possible for, so and the options are, it is possible for the current to be oscillatory. The voltage across the resistor at t equal to 0 plus is 0. Is it so? The right at the beginning, as we very well know, the inductor is a short, it's an open circuit, so no currents can flow, so the voltage across the resistor is actually 0. It is possible for the current to be oscillatory to some extent. Okay? It's not actually oscillatory. It is slowly charges to that is the current slowly builds up. Okay, but of course there might be some kind of that may be considered as an oscillation. Okay, the energy stored in the inductor in the steady state is 0. That's not true because the energy the inductor has already collected some energy. Okay, half Li square. The resistor current eventually falls to 0. No, the resistor current actually builds up to a final value because the inductor shorts out. Okay. Okay, so now we move on to yeah, I suppose the fact that only B is correct is associated with the statement earlier made is now clear to you. Moving on to the sixth problem, switch in the circuit has been closed for a long time. Okay, but before that, let's look at the circuit. We have a 5-volt source, a 1 ohm resistor, and a switch showing that it's going to get opened. Okay, it was already closed and it was going to get opened as shown by the arrow. And then across it, we are having, across this assembly of 5 volt and 1 ohm, we already had a 1 microfarad and a 4 ohm resistor. So there was an initial steady state when the switch was on, and then there is a transient, and finally there is a steady state. So the transient is actually happening between two steady states. Okay, so that's another important concept that we should know. Transient is something that bridges between the two steady states. There is an initial steady state when either the switch is on or the switch is off, and then there is another steady state coming after the transient. When things have settled down, all the charges have been collected, all the magnetism has been built up, etc. And then we are having a shorted inductor or a open capacitor. Okay, so moving on to the switch in the circuit has been closed for a long time, as we guessed. It is opened at t equal to 0. At t equal to 0 plus the current through the 1 microfarad capacitor. Okay, so at t equal to 0, we realize that 0 plus, we realize that the capacitor is a short circuit. Okay, so there was some earlier there was some voltage across it. Why? Because it had opened out. Okay, when the switch was closed, it had opened out and collected a voltage across it. What is this voltage? It is given by the potential divider with respect to 5 volt of 1 ohm and 4 ohm. So it had of the total 5 volt, it had 4 volt across it. The capacitor was full of charges because the switch was on earlier, and it had 4 volt across it. Now this 4 volt is going to discharge via the capacitor, via the resistor, which is now destined to eat up all the energy that has been already stored by the capacitor, because the switch is open, and so there's no other way for the charges to discharge. So it discharges via the 4 ohm, and how much discharges? 4 volt discharges. So what's the current flowing through the for the capacitor such that it discharges, which is 4 by 4, which is equal to 1 ampere. Very simple problem. Only the concepts are important. Just the concepts will sufficiently guide you through the problem. Okay, so now we move on to another problem where there are certain waveforms, and what is given here is it's a current source which now has a switch across it. Okay, and this switch is going to be opened at t equal to 0 as per the arrow. We also have a capacitor and a resistor in series with this source, and a switch which is going to be made. So there are two switches to operate. One is going to be opened, okay, and the current that was flowing through the switch now will be diverted through the other elements. And because the other switch, that is the switch, the horizontally placed switch, is going to close. Okay, so this is the situation that we have already guessed. Now let us look at the problem. A combination of 1 microfarad capacitor with an initial voltage VC0 is equal to minus 2 volt. Okay, so it already is charged to a particular voltage. In series with a 100 ohm resistor is connected to a 20 milliamp ideal DC current source by operating both switches at t equal to 0, as shown. Which of the following graphs shown in the options approximate the voltage Vs across the current source over the next few seconds? So what was happening earlier was that we had that is the first steady state before the switches operate. We had the current source continuously allowing the current to flow through the short circuit across it because the switch is closed. Okay? And we already had we had VC being charged to minus 2 volts, or the signs can be reversed. Okay, so we had 2 volt here, and it was open. And what happened was that the switch was not closed. Okay, so the whole situation will start from minus 2 volts because the switch, when just after the switch closes, now we see that this minus 2 volts becomes available across the current source. Okay, because the current source is now open. Okay, so and because the switch is just closed. Okay, and so we start off from minus 2 volts. So there are two answers with minus 2 volts as the starting point for the graph. And thereafter, as we very well know, we are having what is called as the voltage changing, okay, based on the discharge of the capacitor. And the discharge of the capacitor through the resistor is going to be such that it is exponential in nature. So answer B is correct. Moreover, the current source is now going to charge the capacitor in the positive direction. Okay, positive direction as is shown. Earlier it was minus 2 volts. Okay, so this minus 2 volts is now going to discharge, okay, through the available circuit, and added to it, what is going to happen is that this capacitor, this current source is going to charge it to plus 2 volts, and all these things happen only exponentially. So option B is right. Okay, of course you can compute the whole thing, but the best way of understanding is to know what is happening. Okay, so what is happening is that earlier we had the current source completely removed from the circuit. Why? Because it was allowing the current to flow through the short available across it. Okay, and the capacitor was sitting idle with the minus 2 volts available across it, but with no provision for discharging. Once the switch is closed, it starts discharging. Okay, and that's the reason why it starts off from minus 2 volt. Thereafter, okay, of course, it may have discharged completely at a particular time, okay, near around the time constant, okay, as offered by RC. But then thereafter, the current now becomes active. The current source now becomes active, and it starts to charge the capacitor in the direction as shown. That is in the direction which is exactly as is shown here, where plus is plus itself. Okay, I suppose this is clear. So moving on to the last problem in this section. We have two diagrams. We have a network of linear resistors and independent sources, and we have a current emerging from it such that there is a voltage drop across AB, as there is a voltage buildup as V given there. And this V and I are now shown in a graph as well, wherein we are seeing that it starts off from 4 milliamps, and then we are having 8 volt. Okay, so there's a load line here. Okay, 4 milliamps to 8 volt. Okay, so what does this indicate? It tells us that there is an impedance associated with the circuit. Okay, with the circuit. And what is that? That's equal to 8 by 4 milliamps, or it is equal to 2 kilo ohms. Okay, I suppose this is clear. Okay, and now it is given. Let's see what is given. The VI characteristics as seen from the terminal pair of this network of figure is shown in figure. If an inductance of value 6 millihenry is connected across the terminal pairs AB, okay, so now we are adding a new thing. Across the terminals AB, the time constant of the system will be. Okay, so this is a practical thing that we do. We try to discharge the energy. Okay, so we are having an inductor here, and we are trying to see what will be the time that is involved for discharging the energy. Okay, so we have 6 millihenry, okay, L, and we also have R as 8 by 4, 2 kilo ohms. Okay, so it's obviously we are having 6 by 2, okay, 10 raised to minus 3 divided by 10 raised to 3, that's equal to 10 raised to minus 6, okay, or micro, and 6 by 2 is 3. So answer A is correct. Okay, very simple. It is just a practical situation that is described here, wherein the load line of the system is given, as also what the system is, and how you can discharge the system is all available in the question. And we have also found out that in 3 microseconds the system will be discharged, and you can perhaps touch it. Okay, I suppose this is what we have learned today. I hope all the concepts are very important. First and foremost, how do you take the time constant? Okay, the 3 steps wherein the sources are killed. Point number 1. Point number 2, then you find out the effective capacitance or effective inductance. Okay, and then you look back from the perspective of the effective inductance or capacitance into the circuit after killing the sources. So you get R as well. And thereafter, it's L by R is the time constant, or RC is the time constant. That's point number 1. Point number 2 that we learned is that both the inductor and the capacitor charge. Okay, if the supply is connected to it via a switch. So on switching an inductor or a capacitor with a resistor, we see that they charge. Okay, the capacitor charges to a voltage, and inductor charges to a current. Okay, so the progression is from an open circuit to a short circuit for the inductor, from a short circuit to an open circuit for the capacitor, because the capacitor is now filling up with charges, and the inductor is building up magnetism. Okay, so this is what is happening. Or in other words, the transient is between two steady states. Earlier, the switch was either on or off, and there was a steady state. And then once the switching happens, then the transient occurs, and thereafter we again have a steady state. Okay, so charging will always give rise to a 1 minus e raised to minus t by tau. Okay, with the final value as the coefficient. Okay, it could be a final voltage or it could be a final current for the capacitor inductor respectively. Discharging will always be again exponential. It will be e raised to minus t by tau. The tau factor we already studied. And so whatever has been finally acquired, okay, let's say it's V0, from there it will discharge. Or it is I0, from there it will discharge. Okay, so you can call this as I0, V0, and from there they discharge. So these are the major concepts that we covered. And based on these concepts, you can do most of the transients. Okay. Finally, I hope we will remember that at steady state, the inductor will always be a short circuit, okay, and the capacitor will be an open circuit, okay, by virtue of whatever has already happened. And the inductor will store an energy of half Li squared. If there's no current flow through it, then it becomes zero. Okay, capacitor will be half CV squared. Of course, it depends upon where it is located. Okay, so this is all for today. We'll move on to for a little more difficult problems soon. Thank you.